This is a dramatic reading of Gotta Get 16 Gamma Girls by the Stand-Up Physicist, a blog available at science2.0.com. I spent a year playing with gamma matrices, sometimes called Dirac matrices, in a relativistic quantum field theory class at Harvard University. And it was kind of like being at the World Economic Forum at Davos, Switzerland, and thinking that I got no money, I got no power, like what am I doing here? Totally outclassed by all these people and all this money in just so many different ways. You know, I've never been invited to talk about economics or physics for that matter. And, you know, I go back and I look at that field theory class and I just, you know, got to scratch the old head and say, you know, really, what was going on there? You know, calculations were done, and they do match the data, I mean, as far as we did in the class, but that's not what really goes into the work, because then supercomputers had to take over to do all the permutations that that could occur. And in fact, it sometimes takes several weeks of calculations by these supercomputers on just super huge data sets. And, you know, I think that only the smartest of the smart kids actually get it. And it actually makes me wonder if they're bluffing. Now, by the end of this video blog, I hope you can do 3 things. First, from memory, write down all 16 gamma matrices in a quaternion representation. I actually can't do that with the standard, you know, gamma 0 to 5 combined with sigmas. I just can't do it. Second, I want you to be able to collect these 16 gammas into 3 separate groups. And third, I want you to have a visual sense of what they're doing to patterns of events that appear in space-time. Once Minkowski figured out that special relativity was about 4D rotations, people considered using quaternions as a natural candidate for the job, since they do 3D rotations already. That approach just didn't work. So they decided to actually kind of cheat and throw in another factor of I that commuted. In my own survey of the work on quaternions, at least before the mid-90s, everybody used biquaternions. They throw in that extra factor of I. Now, I know they're not really cheating because, you know, they spell out their rules really clearly, but I reply with the knights who say "nee," and not N-I, but N-E-E, and not elegant enough. Now, Stefan DeLeo was working out of Lecce, Italy, which is actually in the heel of Italy, and he worked up a few papers in the mid-90s about using real value quaternions to do the heavy lifting seen in physics. For example, in 1995, he wrote a paper called Quaternions and Special Relativity, showing a way to do the job with real valued quaternions. And while I was able to kind of like nod along, I wasn't able to write, you know, code for how to implement the proposal. So the way I work, I really didn't get it. If I get it, I can program it. The important message, though, was that it was doable, okay, with real value quaternions. Because everybody before then said, no, I got to bail. I got to throw in an extra factor of I. Now, there are some advantages to owning quaternions.com as I do. People presume that I'm a professor, and sometimes want to discuss their own work in these areas. I mean, who would do this just for amusement? Well, Jose Luis Lopez Bonilla of Mexico City got his PhD in theoretical physics. And he's got 4 kids, and he now works for a telecom company. But he sent me his two-page paper of his. Now you can't get too in-depth in a mere 2 pages. But there was a great table that mapped one way to write 16 quaternion matrices with the one way to write them with a quaternion representation. So what is that one quaternion way? Well, there are 4 basis vectors for quaternions, and 1, I, j, and k. Now, if there is a quaternion that you want to, hit up with the gamma matrices, then what you do is you pre and you post multiply that matrix by these basis vectors. And there are basically 16 ways to do that. No more, no less. And I bet you can even memorize that because it is so simple. Okay, but the most important one was the one that goes 1q1. Because classical physics and classical quantum mechanics use only that one. And that's most of physics. It doesn't change a thing. I kind of like that. All right, now, what would the groups U1 or SU2 look like if I hit it on both sides with these, 16 different quaternion gammas? The animation would remain the same. I mean, there's a circle, and that's the kind of U1 thing, and then SU2 is a sphere, and all this would do is kind of map points to different places on those various circular objects, and the complete picture makes a complete set, and you really couldn't see any difference by using one or the other. Bummer. So what I decided to do was to think of using a smaller collection of events, and because sometimes by looking at less, your mind can see further. So we'll see that. So here's an animation of an inertial observer generated by adding the same number over and over again. Not too interesting. Gammas come up in the context of the standard model. So I decided to map these straight and narrow events to an animated unit sphere by just taking the norm. Now this is more fun. Every event shown has a norm of 1. This collection of events starts with a pair running away from each other before one quickly disappears. The long-lived event goes out, stops, and takes a step towards the origin before disappearing. The shadow underneath the all states graph in the upper, let me see if I get this right. No, I can't get this right. Is it right or left? I think upper left corner. It shows it's the shadow that shows it's a curved path in space. Kind of interesting. All right. Now, the next gamma quaternion matrices to consider, I'm going to call the diagonal gammas. So they are IQI, JQJ, and KQK. There are these at least put the 4 variables back where they belong. Now it's not quite exactly where they belong, or there is a change going on there. As you can see, 2 terms flip sign, time and x, and the other 2 terms they keep their sign. So that's kind of neat. And here is the animation. The diagonal gammas are in orange, which unfortunately looks an awful lot like yellow. Okay, but in the complex plane, there is this one orange line that kind of completes the oval, and the other that is actually a time reversal of the input. It's going backwards in time. If there are these completers. Oh, why does that yellow dot seem to be kind of out on her own? Well, these three animation points are made up of one completer plus 2 time reversals. So now we're only looking at one here. Actually, it is actually the IQI animation. And so there is the conjugate going on there. Actually, it's not only a conjugate, but it's a time reversal. And that's how you complete the circle. And the double, and in the up, down, plus time, and near, far, plus time complex planes, that would be the stuff on the right, only time flips sign. So you can actually spot the time reversal quality if you watch this carefully. All right, the first thing the yellow does is a 2-particle runaway until it's gone and does the loop back. And then if you look at the end of the animation, you see the orange is doing one of those quick particle things, okay? It actually starts at a loop back kind of move. So that's why that really is time reversal. The next set of quaternion representations of gamma matrices, fancy, I call the 1 gammas. And here the information is getting scrambled because it's 1, the quaternion I, 1, the quaternion J, 1, the quaternion K, and then the reverse of those, I, the quaternion 1. And here, take a look at that. Hopefully you can see that. And you go, okay, so time has traded places with X and switched its sign, and Y has changed its place with Z and switched its sign. Oh my goodness. So let's take a look at that and make sense of it. No, I don't quite understand this. Well, you know, that's not so bad because, you know, we're dealing with relativistic quantum field theory, which is a difficult subject. Why shouldn't the animations be difficult? So the final set, I call the cross gammas. There's 6 of these because it goes like IQJ, IQK, and JQK, and then the reverses of all those 3, and you know they're just as scrambled up as the 1 gammas. So now we can put this all together. And what do we see? Too much. Okay. We actually see 4 groups of 4. Okay? So the 16 gammas take 1 path in space-time and generate 15 other paths of events. So the sum of all possible histories, which is what the kind of calculation that goes on in quantum field theory, may just look something like this or related to this. The animation has the look of relativistic quantum field theory. You know, many particles at once doing things that I'm probably not bright enough to understand. So, have the goals, the lofty goals we've set, have they been achieved? Well, first, can we write out all 16 gamma matrices by just doing this quaternion triple product thing? I think that's doable. And second, do we have a groupings of these things? We've got the diagonals, we've got the ones that have a 1 in them, and we've got the cross products, so that's not bad. And the visualizations, well, at least they're there, even if we don't understand everything in there, but that wasn't the goal. The goal was kind of get a sense of, oh, I'm taking 1 path, I'm making a collection of 16, and somehow I'm going to have to work with those. So here's my snarky puzzle. At the ICC 8 International Clifford Conference, the 8th one, in Campinas, Brazil, I pitched the Quaternions plus California Ring program to Professor David Hestenes of Clifford and geometric algebra fame. But he was a seasoned vet. And this sounded like an old and bad dream to his ear. Quaternions are just a bit player. They're CL02, if you want to sound really bright, within the larger C of Clifford algebras. The real numbers are CL00, which makes them a subgroup of quaternions, and the complex numbers are CL01, and also a subgroup of the quaternions. The gamma matrices, oh, they reach beyond. They are this Clifford algebra CL13. Oh, and according to this post, they can be represented as quaternions. Now, in another snarky puzzle, I showed how to represent the Lorentz group using real-valued quaternions. So quaternions are also intimate friends with 4-pi rotations needed for spinors. So what I want you to do is list all those important things quaternions just can't do anymore. All right. Good luck. Bye-bye.